to implement Gaussian quadrature in 2 dimensions. So I first define the function that has been transformed to the limits -1 to 1. So I define g uv function, and it should return a value, the natural log of zero point 0.3 times u plus zero point 0.5 times v plus 4.2, and that's it. Okay, function has been defined. Now I define the constants. Okay, I define u as numpy array. So I require 3 values. So it is -0.774596. This is from the table of Legendre coefficients for Gauss-Legendre rule. These are symmetric values, and for this array, this is equal to v equal to u, right? Now I define the constants, cu constants. They will be equal to 0.55555 something, and then the other constant is 0.8888, and then again 0.55, and then cv will be equal to cu, right? They can be different, but this is, in this case, the grid we have considered as a square grid. Now we have to compute the summation which was written above. Yes, here. Yes, we have to compute this summation, and when we transform this integral, so there was a constant 0.075, because the original integral was uh, log of x plus 2y dy dx. So this constant will also appear at 0.075. Okay, so let's implement that summation. So I write GL Gauss-Legendre summation equals 0, right? Now for I in range 3, we are considering 3-point rule, and for j in range 3, Gauss-Legendre sum is equal to Gauss-Legendre sum plus plus CUI times CVJ times V of UI V. This is the end of inner loop, and there is the end of outer loop. Then the discrepancy, which was the constant 0.75 times VL sum, and print the value of VL sum. That's it. That's it. Two-dimensional integration by Gauss-Legendre rule, right? So let's run it and see the answer. Yes, 0.42955. Let me show you the original problem that I have just solved in front of you from the book, if my computer allows me to open. Okay, so this was the problem. This is the problem. Log of x plus 2y dy dx, and I have we transformed into variable u and v so that our limits conform to the condition of -1 to 1, and then the coefficients have been adopted, and the simple summation. I have used slightly different notation than the used by the book, and to me that was the nice addition. And see the conclusion. Uh, this results this result requires only 9 functional evaluation compared to 15 for the composite Simpson's rule considered in the same example. It is accurate to within 10 to the power minus 9 compared to 10 to the power minus 6 accuracy, right? So Gauss-Legendre rule is the practical rule for doing that. Now, if you see what is available in Python, so as a matter of concluding remarks, so in the SciPy library, the integration functions are available. So you have the quad function, the double quad for double integrals, triple quad for triple integrals, and you have the quadrature function, you have the Romberg integration. So now you will be much more confident while using these routines, even if you have not developed them by yourself. So for example, if you look for the double quad, so it looks for the function definition a, b, g function and h function. Well, this is going to treat the variable limits as well. Whenever we write a double integral, the outer limits are constants. The inner limits can be functional in the form of a function. So it is more generic one. And see the convergence bound set by the software, 10 raised to the power minus 8, 10 raised to the power minus 8, right? So with this, I hope that you will keep on exploring the numerical integration, and whenever it is required, you will never make any excuse that you cannot solve it. Now you have the ability, you have the free software uh, to attempt these problems.